The speaker is Lue Pan from Princeton University. He's going to talk on the locally analytic vectors of completed cohomology of modular curves. Let's welcome.
Is it good? Okay. Yeah. So thank you. So many thanks for the invitation. It's my great pleasure to speak here. I've been to Ohio several times when I was a kid, but it's first time talking about math here. Yeah. So I want to just give a survey on some recent results. It has been several years on the locally analytic vectors of completely cohomology of modular curves. So let me first just explain some motivation to study. Well, I will give a definition, but let me first just say what's the motivation to study this. So throughout this talk, P will be a prime number. And so Fontaine and Mazur made the following conjecture last century, which is part of the long-dance program. So let me put all of their names here. It says the following. So if you have a two-dimensional Galois representation, you look at the absolute Galois group of Q, mapping to GL2 QP bar. Okay, so the QP bar denotes algebraic closure of QP. Let me just assume this is a continuous and irreducible representation. And this conjecture just predicts one this representation comes from a modular form or cuspidal form. So it was known before that. So this Galois representation has to satisfy first it is almost unramified as unramified at almost all finite many places for almost all prime L, and it has to be odd, which is some condition at the infinite place, which just means that the determinant of the complex conjugation is -1. So there's a complex conjugation. So it's an order 2 element. So in particular, its determinant is either 1 or -1, and you require it to be -1. And the last condition is the most important one. So without putting the third one, so you will get too many Galois representations. So the last one is requiring at the place P. Okay, so the same this P. It is the ROM, okay, in the sense of Fontaine. And let me normalize it. So of Hodge-State's weights at 0 and k, where k is a non-active integer. Okay, and then the conjecture says that if you have such a Galois representation, then rho comes from an eigenform, so a modular form of weights k plus 1. So here it comes from a modular form, just means that so you can find the eigenform with Q expansion, let's say in Q to the n, and so after fixing identification between complex numbers and the p-adic numbers, then you require at almost all L, this Fourier coefficient matches with the trace of the Frobenius element. That's for L. So because of the first condition, this is well defined. Okay, so that's what I mean by it comes from a modular form. Okay, so if you have never seen this conjecture before, so So sometimes people call this one-street condition geometric because if you take a Galois representation coming from p-adic cohomology of some smooth projective varieties over Q, then it satisfies one street. So in particular, for example, you can take an elliptic curve over Q and look at how the Galois group acts on its first cohomology or the Tate module, then you will get such rho. And then this conjecture just predicts that actually it really comes from modular form. So in the special case of the elliptic curve, is just the Taniyama-Shimura-Bay conjecture, now a theorem. Okay, so I should so this is the motivating conjecture, but actually this conjecture, actually for most cases, actually we know this conjecture, but still, so at least for me, I want to revisit some part of the argument because so certainly you can ask, you can generalize this conjecture. You can replace Q by arbitrary number field. You can replace Q by larger number, and then we basically know very little about that. So one very successful approach to this conjecture is by Emerton. So Matt Emerton approach. So there are two steps. Are there other questions? Or? Okay. So yeah, there are just two steps. So first is instead of you just show there exists a modular form which matches a rho. By the way, where you can see the time. Okay. So you first show rho comes from a p-adic modular form. So or a p-adic limit of modular forms. So concretely, in some sense, it means that so you can take a lattice of this representation and just mod some power of p, and you just ask this after mod p to the n, it comes from some modular form. Might not be the same modular form, but for each n, in some sense, it's congruent to some modular form. So this is of course much weaker than asking it actually comes from modular form. And actually, so what we expect is that if a representation just satisfying 1, 2, they all come from such a p-adic limit. Okay, so the second step definitely need to make use of this assumption. So just show that this de Rham property implies that rho comes from not a p-adic limit, but the actual, maybe let me just say classical modular form. So yeah, so when I usually talk about this, so if you think about finding a modular form, it's like solving some kind of a differential equation. So the first step, in some sense, is like finding weak solution. And okay, so because you just show the solution in some completion of some function space, some p-adic completion. But the second step is really you want to make use of the condition you put on your equation to show the regularity of your solution. So the main focus of this talk is actually the step 2. So I won't say anything about the step 1. So, but I want to say, well, how to better. So maybe basically a new proof, a new argument for this second step. But before doing that, so I still haven't told you what I really mean by p-adic limit of modular forms. So in this subject, there are many notions of PID modular forms or automorphic forms, and what Emerton used is the so-called the completed cohomology. Actually, he introduced a completed cohomology to really attack this conjecture. So let me just quickly explain what is the completed cohomology. Okay, so well, of modular curves, so of course, I mean, Emerton introduced a quite great generality, but in this talk, I will just restrict myself to the case of modular curves. Okay. So let me introduce some notations. So if you have some neat open compact subgroup of a GL2 of finite adels, and then we have the analytic modular curve with level k, which is the algebraic curve, a fine algebraic curve over Q, and this is something defined over Q, but its complex points can be written as the usual double quotient. So the union of upper and the lower half plane times GL2 finite adel, right quotient by K, and left quotient by the Q points. Okay. And as we, I mean, a classical result tells you that actually the cohomology, there are some naturally defined local system on it, and the cohomology essentially gives you modular form. So we will just look at this cohomology. In the completed cohomology, the idea is that so we fix. So usually you can write this level as you can separate the level away from P and at P. So this KP is just inside GL2 QP. And the idea is that you just vary this this one. So let me just erase this one. So I will fix. So throughout this talk, that this will be fixed. So the definition is as follows. So once you have a KP, you can look at the modular curve with level K upper P, K lower P, and you can just take its torsion coefficient cohomology. And you usually just take the inverse limit over n, but now instead of doing that, you first vary the level at P, and then you take the inverse limit over n. Okay, so this is the completed cohomology. Here I told you, so it really comes from a p-adic limit on modular form. So actually, in this case, there is some equivalent definition. You can simply just take the finite level one. Okay, so just the ZP coefficient, and then you just take p-adic completion. Actually, both agree with each other. So you see, actually, it's just some kind of p-adic limit of the classical cohomology. So for this talk, I will ignore the torsion. Actually, it's torsion free, but I will just invert P all the time. And it turns out this is a p-adic Banach space. So from this point of view, it's clear. And there are several symmetries. So first is that there's an action because it's defined over Q. So there is an action of the absolute Galois group. And also because I take the dark limit over all level at P, so then you have an action of GL2 QP. And also you can, there are also, because I fixed the K upper P, so there are Hecke operators away from P. So I'll just put here T denotes the Hecke algebra, spherical Hecke algebra. so now I can really say what step one really just means that you just show that the rho appears as a sub. So this is a big representation. If you just ignore these two parts, so this is a big representation of the absolute Galois group. The step one really just ask home of rho as a GK as a Galois representation. It appears as a sub. Well, I forgot to say so. Even though this you can define for any degree, but the interesting degree is just one. So I would just look at the H2 top 1. So QP bar is non-zero. So step one really just ask, it appears as a sub-representation. And I will just focus on step two. So assuming that rho is a sub-representation, what can we say? So it turns out the key is understanding. So I should say, so you have these three symmetries, but of course, I mean, they commute with each other, but actually they are not independent. So what you really need to understand is actually the interplay between these actions. So for example, so what Emerton did in his work is that well, let me first say ignore this. So in this absolute Galois group over Q, you have the decomposition group at P. So Emerton in his work, so he established the so-called local global compatibility, which tells you how this local group Galois group action interacts with this GL2QP action. So he used the so-called Piedic local Langlands correspondence for GL2QP, which really to understand these two actions, and use this to really prove this in the so-called regular case. I don't have time to really say more about this Piedic local Langlands correspondence, but it's a very beautiful result. So just tells you there's some natural correspondence between two-dimensional Galois representation at P and some Banach unitary representation of GL2QP. But the problem is that it's not really a problem, but let me just make this. The first remark is that so we only have Piedic local Langlands correspondence so far for GL2QP. So I should say, so Emerton, I mean, this result is from more than 15 years ago, and at that time we only have Piedic local Langlands correspondence for GL2QP, but still now we don't know. Well, we don't have a very general Piedic local Langlands correspondence for example, you just replace 2 by 3 or QP by its extension. We don't have that generic correspondence. So it makes very hard to generalize this argument. If you, as I mentioned in the beginning, if you want to try to attack the conjecture beyond the GL2Q, then we don't have this ingredient. So we don't have GL2QP. So at least for me, it's a bit unsatisfying. And the second remark I want to make is that Emerton's this approach only works for so-called a regular case. So let me just remind you. So the Galois representation, I mentioned that because it's two-dimensional, so it has two Hodge-state weights. One is 0, one is a non-negative integer, and so the non-negative integer I mentioned. Sorry, I think I used the letter k to denote it, and so regular simply means k is not equal to 0. So another way to say this is that irregular just means k equal to 0, and k is not 0, then we say it's regular. In this case, you have two distinct Hodge-state weights, and it turns out both the series of Galois representations and also the series of modular forms. So in this case, 1k is 0. So if you remember, so it should correspond to weight 1 modular form, and the series of weight 1 modular form is very different from weight at least 2. So let me just separate these two cases, and actually Emerton's argument only works for the regular case. So again, it doesn't sound very, at least for me, not satisfactory. But I should say, even for weight 1 case, for the fundamental conjecture, we know a lot. That motivates me to revisit this second step, but not trying to use much p-adic or local long-length correspondence. Yeah. So I should say that so this is some, well, you can say this is a purely resulting in representation theory. So it doesn't use any geometry at all. But if you look at the definition of completed cohomology, it's a cohomology of some very nice symmetric variety, algebraic curve, and you don't use any geometry of it. So the result I'm going to present is, the argument or the approach I want to present is really to make use of the geometry of these nice curves. And so I'm going to erase this part. There are other questions before I do that. So maybe I should first say what's the punchline. So I already mentioned I want to use a geometric method, but what do I want to achieve using geometry? So here, again, so as I mentioned, the key is to understand the interplays between these actions. But so this is a nice p-adic Lie group. This is some profinite group. So we all learned in Lie theory classes that it's much harder. It's much easier to understand the Lie algebra action than the actual group action. So it turns out actually for the purpose of just, for example, fundamental conjecture, it's enough just to understand the Lie algebra action. But of course, to talk about Lie algebra action, so this is a p-adic Banach space. Let me write it down. So p-adic Banach space. Infinite dimensional. So if you want to talk about the Lie algebra action, at least you need to know that locally around the origin, this action, you can take a derivative. But this is not automatic because we are in infinite dimensional setting. So the first thing you need to do is that if you want to talk about Lie algebra action, you need to restrict to those vectors on which Lie algebra act. And that would appear in the title, the locally analytic vectors. So let me use LA. This denotes locally analytic vectors. So inside this completed cohomology. So maybe it's better to say GL2QP locally analytic vectors. So concretely, it just means that so this is a p-adic manifold, and you look at those vectors on which this action can be locally around the origin can be expressed as a convergent Taylor series. So, a priori, it's not clear this is well, there exists any non-zero vector here, but actually it turns out in this case it's a dense subspace. So you don't lose much information. And actually, it's much stronger than dense. So what Schneider-Teitelbaum showed that for any GL2QP, so invariant subspace, the locally analytic vectors are dense. So in particular, you really don't lose much information. So for example, if rho appears here as a subrepresentation, it also appears here as a subrepresentation. So we can just look at this subspace, and now instead we want to understand this. So now the Lie algebra of GL2QP action on it. So which is nothing but, well, just we use the little GL2. Its action. And as I mentioned, so it's not enough just to understand one single action, but you also want to understand this action of the Galois group. So in some sense, we also want to understand how the Lie algebra of this Galois group acts on it. So, a little bit, it's not a precise statement, but the idea is you really just pass to the Lie algebra level now. Okay, so now how to understand this Lie algebra action? So the punchline here is localized. You localize the locally analytic vectors of completed cohomology. So what do I mean by localize? So this is in the 80s of the last century, so Billings and Bernstein introduced a very powerful geometric method to study representation of the algebra. So again, I'm not going to give a very precise statement, but the idea is that on the one side you have you can look at the representation of the algebra. So this is the universe enveloping algebra. Okay, and then you can try to localize it. So why the localization to some D modules, or possibly twisted D modules. I'm not going to, yeah, it's not a precise statement. So twisted D modules on P1. I mean, P1 shows up here because this is the flag variety. For GL2. Okay, so and you also have a functor going other direction. Is once you have some D modules, then you can take the global section or take the cohomology. Okay. I'm not claiming this is both functors inverse to each other. So I'm just saying that so the procedure of localization just transforms just a Lie algebra representation to something much more geometric, and then so on D modules, then on P1, for example, you have P1, you have a stratification, then you can use more geometric tools to study it. So here is the same. So we want to understand this completed cohomology, which is some module over it, and it would be nice if we can localize it and get some D modules on P1. And it turns out actually there's a very simple, I mean, it's not easy to, the proof is not simple, but the construction is simple to localize it. So let me just, so this is just some motivation. So now here's the construction. Maybe, so I need to introduce some more notations, but so for the, so for level K modular curve, so I can take its compactification and get a projected curve and base change to CP, where CP denotes algebraic closure of QP, and then you take p-adic completion, and view as an adic space over CP. And So recall that this is constructed by varying level at P. So I can just also vary level at P of this tower and get this is the inverse limit of O finite level modular curve. So now I just vary level at P. So it turns out that this inverse limit exists in the world of perfectoid. Exists as a perfectoid space. So actually, we don't need that, but sounds like a nice geometric object. And so you should regard as this is an infinite level modular curve. I mean, when I say infinite level, I mean infinite level at P. So modular curve is infinite level at P. So it has an action of GL2QP. So I forgot to say, so this is what Peter Schulze proved. And moreover, so it has a nice period morphism denoted by pi HT, pi Hodge-Tate. Okay, and mapping to P1. And so which is so P1, as I mentioned, so it's GL2, the flat variety for GL2. So there's a natural GL2 action, and it turns out this is GL2QP equivalent. And so you can just take this as you can just consider the structure sheaf of it. Okay, so this denotes the structure sheaf, and you just push forward along this this period morphism. Okay, as I mentioned, so this push forward is GL2QP equivalent. So in particular, so it's a GL2QP equivalent sheaf on P1, and then you can take the locally analytic vectors here. Okay, so let me call this OLA. And so this is a nice GL2QP equivalent sheaf on P1. So I claim this is like the localization of the completed cohomology. So the more precise statement will be, but this is the construction. So. That's a good question. So far, I don't think we really have p-adic localizations. But I do expect that once we have that, it should be. Yeah. Also, this is really not the one fixing central character or infinitesimal character, so it's a bit subtle. So. But yeah, that's a very, very good question. Any more questions? Okay, so theorem. This is something I proved several years ago. Is that so? First, well, as I mentioned, so this you get back to your Lie algebra representation by taking cohomology. So first is actually the cohomology of this. There's a natural isomorphism between its cohomology and the completed cohomology, the locally analytic vectors, once you base change to CP. So that's the first statement. And second is that, well, as I mentioned, so this is some D module. So D module just means the differential operator is on P1x on it. So, and actually, it turns out it's not local. It's not a D module on G mod B Borel, but actually some kind of D modules over G mod N, the unipotent. So more precisely, so this is some D module or D tutor module, some version without fixing the infinitesimal character. So more precisely, so I need to introduce some notation. So as I mentioned, so P1 is the flat variety. So in particular, So if you have a point, then you get a Borel subalgebra inside GL2. And let me use Bx to denote the corresponding Borel, and Nx is the unipotent radical. So in particular, you can just glue the Bx at each point and just get a horizontal Borel. So for example, so one way to make this more precise is that you look at P1 as the GL2. So this is a constant, the constant vector bundle. And inside this, I have the, let me call it B circle, which is just, as I mentioned, so a union of, just at each point is the corresponding Borel. Okay, and moreover, I can also consider just the unipotent one, so it's just the union of all the Nx. And so this Lie algebra acts naturally on this sheaf OLA, and it contains OP1 as a subsheaf. So you can extend this Lie algebra action OP1 linearly to add actions, or just acts on your sheaf. Okay, and it turns out that if you restrict your action to this subline bundle, so it's only one dimensional, it turns out that the action is trivial, so and not annihilates. OLA. So another way to say this is that this locally analytic vectors, this infinite level functions, when you take the locally analytic vectors, it satisfies some differential equation. So as I mentioned, so this is rank 1. So locally, it's just just one first order differential equation. And I tend to think about this as some kind of p-adic Cauchy-Riemann equation. And this one comes from, you only get one equation simply because you are working over a curve. So that in some sense just means that you can localize it to G mod n. So that's the intuition behind. And once you localize to G mod n, so once it has a map to G mod b, and this is a tensor of the torus, diagonal torus. And this torus, of course, diagonal torus just acts on everything. So you get an induced action of this torus, so it's Lie algebra acts on everything. So concretely, so you can look at, because n naught acts trivially, so the action of this b naught factors through this quotient, and you can just look at this. The global section, of course, just acts on it. Okay, so actually, it's just as I mentioned, it's just nothing but the Lie algebra of this torus. So just I will use H to denote the Cartan quotient. So you get such an H action. So, and it turns out that this H action encodes both. I erased that, but well, it's here. So encodes the infinitesimal, the center of the universal enveloping algebra of GL2, and also the somehow the center of this Lie algebra action. So encodes action. Okay, I don't have space. So here, action of once is just the center of the universal enveloping algebra of GL2, and also the so-called Sen operator. So this is some operator introduced by Sen, which describes the Hodge-Theta structure of a p-adic Galois representation. So, for example, the Hodge-Theta Weta I mentioned really just nothing but the eigenvalues of this operator. And one sort of way to think about this is in the center of the Lie algebra of the absolute Galois group of QP. At least you base change to CP. Okay, So it's not a precise statement, but you can make it precise. But it's some kind of infinitesimal character for the Galois group. So so you see that's you see this actually this you construct such action, and it encodes both this action of the GL2 and also the Galois action. So that's how you actually you can see some what I mentioned, some interplay between these two action. So I should mention that all these results. So I just let me erase and just make a remark. So I mentioned this in the case of a modular curve, but actually the construction work quite generally for arbitrary Schmal variety. So for general Schmal varieties, this was done by Juan Esteban Rodriguez Camargo. So actually, if you just do the same construction, and it will satisfy these conditions for general Schmal variety. And I should also mention that, so I would just say this verbally. So this differential equation, also there is much more general theory behind of this called the, well, nowadays people call geometric sense theory. Okay, so I mean, it has nothing to do with nothing to do with modular curve Schmal variety. It's really just something to do with, I mean, just the p-adic geometry of rigid analytic varieties, and well, which is also quite active area nowadays. So, but yeah, I won't say more than that. So it turns out once you localize the completed cohomology to some sheaf on P1, then you can try to study the geometry of this sheaf. I mean, I should also mention this geometric sense theory also actually tells you how to, for example, describe the Lie algebra action on it. So actually, it's not that. So I wrote in some. I give the definition. It looks a little bit complicated, but actually, you know a lot about this. So then you can try to study the geometry of this sheaf and try to use that to prove results for the complete cohomology. So now, maybe the key point is that whatever you want to achieve here, you can first ask whether you can do this on the sheaf level. Whatever, for example, if you want to construct some operators here, you can ask whether you can construct already on the sheaf level. You can localize it. And it turns out to be quite successful. So let me just mention two applications which answers, well, not answer, but just applications to something to do with the von der Maser conjecture. Maybe before doing that, other questions for this theorem? Okay, so application one is, so this is something you can try to study, which is so this B denotes the constant Borel. So this is the Borel subalgebra inside GL2. Okay, and once you have a weight, it's a weight. Then you can view mu as a map from B. First, you quotient by the unipotent radical, and then mu induces a map from B to, let's say, CP. Application one is actually you can just calculate the mu eigenspace isotropy part of the completed cohomology. vector base change to CP. Maybe I should say, so why do we care about this? Of course, in representation theory, Lie theory class, so we know that it's very natural to study highest weight vector. But if you think about completed cohomology as some kind of a generalization of a classical space of automorphic forms, so in some sense you are calculating some B cohomology. So let me just mention the analogy here is that the PK cohomology of automorphic forms, space of automorphic forms, actually calculate the coherent cohomology of Schmal varieties. So in the case of GL2, it's just related to modular forms. Okay, and here we are doing similar things, but for p-adic one. So we are just doing B cohomology and ask, well, if I replace the space of automorphic forms by completed cohomology, what do I get? The answer is it's a little bit hard to describe, but I would say so. The result is that actually this is related to so-called overconvergent modular forms, which is some generalization of modular forms. Most overconvergent forms are not classical modular forms. So the intuition is that the classical modular forms are defined everywhere on the modular curve, and overconvergent modular forms are just functions or sections defined on some locus. Okay, so it might not be it's only just defined on some locus, so you might not be able to extend it to the whole curve. So that's why there are a lot. And so not only overconvergent modular forms, but also some higher overconvergent modular forms. So as I mentioned, so if you think about overconvergent modular forms as some sections of some line bundle on some locus, then you can of course also take the cohomology, like the local cohomology over this locus or its complement. So it turns out that actually you can just express this in terms of higher overconvergent modular forms, and you shouldn't be surprised that this higher will appear, because if you think about this, so as I mentioned, now you can use geometric tools to study OLA, and once you look at the action of the Borel, the group Borel, it acts on P1, and you get the natural Broughton stratification, and each stratification will contribute to some cohomology, and then you naturally get this description. Okay, so it turns out that once you have done this, then actually you can use this to, once you take mu to be the singular rate, actually you can use this to study fundamental conjecture in the irregular rate. So application is, for example, let me just mention corollary. One corollary is that overconvergent eigenform of weight 1 is classical if I didn't give a name, rho f, f if the attached Galois representation is the ROM. So now, as I mentioned, so Emerton's approach, so for this one, weight 1, so this is an irregular case. This is corresponds to the k equal to 0 case. So his method does not work in this case, but now you can actually make it work. In some sense, you use p-adic local long lines first to construct the overconvergent eigenform. Then you use this result to show it's actually classical. So actually, this proves a lot of cases of fundamental conjecture in the irregular case. And I should let me just make a remark here. So this idea of first constructing an overconvergent form, then trying to show it's classical is not new actually for proving classicality of weight one form. So actually it goes back to the classical work of Bowser-Taylor in the ordinary case. But here, so this method, I would say, is more conceptual and actually works quite generally. Yeah. Well, yeah, I don't have time, but there are many developments after Bowser-Taylor's work. And I also want to mention that do I want to say? Yeah. So on one technical level, so this is remark one. Remark two is that so this is in the case of modular curve. In modular curve is it's the moduli space of an elliptic curve. Then you can look at moduli space of a abelian surface. And in that case, you can also try to do similar things and prove classicality of some overconvergent modular form or ordinary modular form. So so quite recently, so Boxer, Caligari, and OBG, and Vincent-Fioni, they extend in some sense this result to the case of Ziegel's threefold. So I won't tell you the weight, but I will just tell you the underlying Schmal variety. And actually, their motivation is that to actually use this to prove modularity or von der Maser conjecture in some sense. In this case, so what they actually can prove is they prove some so modularity of abelian surfaces over Q. At least they can prove some positive proportion of it using this. Yeah, but just by generalizing this type of argument to the case of Ziegel's threefold. Okay, so this is application 1. In application 2, so as I mentioned, so in Emerton's approach, he used the p-adic local long-length correspondence. So it turns out that using this approach, actually, you can not only get rid of p-adic local long-length, but at least for the second step, also you can reprove results in p-adic local long-length. So I don't have time, so I would just say you can actually describe, as I mentioned, so rho appears in your completed cohomology, so this home is non-zero. And as I mentioned, sir, the key point is how to describe this GL2QP action. So it turns out that using this after using this localization, and you can, well, with some extra work, you can really describe this GL2QP representation geometrically. And so, for example, it just proves, for example, it proves that rho is classical in that. And actually, as I mentioned, so reproof results in p-adic local long-length correspondence for GL2QP. So, yeah, sorry, I forgot to say, in this case, it's regular. So in the regular de Rham case, so people have some description of the GL2QP representation before, or conjecture before, but later proved by different group of people. Yeah, actually people, well, I should mention, so especially Behe, he needs to separate the case of principal series and the supercuspidal. But it turns out that both cases can be uniform. You can formulate the structure of this in a uniform way using this geometry method. And for example, even just to reprove some results which is not easy to prove in the past. And so I should say, so what the key point here is that yeah. So in the regular de Rham case, in general for the de Rham representation, so one way to characterize it that there is some operator introduced by Fontaine, so I would just call it Fontaine operator, is equal to 0. So that's one way to characterize the de Rham representation. So you can imagine the key is to understand this Fontaine operator. So it turns out you can localize Fontaine operator. So I mean, a priori, it only acts on some operator on the level of cohomology, but actually you can realize it on the sheaf of on the sheaf level. And actually, it has a very simple description, and so that you can really read information from that description. So the last remark I want to make is that several remarks. So first remark is that it's natural to ask well whether you can generalize this to more general small varieties. Unfortunately, at least I can't do it. But for example, for Hilbert case, very recently, Yuan Yang, Jiang, a student of Vincent Thioni, so can generalize this part to the Hilbert case with parallel weights. And for example, so it gives some description of the representation of GL2 appearing in the Hilbert in the completed cohomology of a Hilbert modular variety, and I think some properties are not known by other methods. And also, I want to just mention that even if you just care about over Q, so as I mentioned, so far this seems to be a reproof of some result for in GL2Q. But actually, you can, instead of doing Hilbert, but you can just look at the Schmor curve case, still GL2, but with associated to a quaternion algebra. So it's some quaternion algebra, but now you look at quaternion algebra ramified at P. Okay, so at P you get a representation of the quaternion algebra, not GL2QP action. So you can't really use PID local long-length correspondence to study it, but this method works equally well in that case. So the step 2 I mentioned in the beginning also works in this case. So I think even for this case, this is something new. So, well, I would say just over Q, but yeah, there are also results over more general totally real field. But yeah, let me just stop here. Thank you.
Okay. Any questions? Okay. Any questions?
Yeah. So you mentioned the localization of Bernstein balancing localization. So is there any relation with the work of Actok Wasley?
Yeah,
this localization.
Yeah, I expected this OLA some sort of due can be, agrees with the localization of completed cohomology of that. But also in their work, I think they also fix the infinitesimal character. And here, completed cohomology is the one you don't fix that. I'm not sure they have a version for
So fix the inf.
Yeah, you fix the infinitesimal character.
Okay.
But I think they fixed that so that, for example, you really get the D module over P1. I suspect that maybe in that case you can really prove prove some isomorphism, but I don't think they have a version without fixing infinitesimal character.
Okay, other question?
So here, can you say something about this analogy here?
It's really just a analogy. So it's really, you see this, so this PK cohomology really picks up. Yeah, you must know much better. So you compute coherent cohomology of Schmor varieties. So here I was just saying that you forget about K. You just look at P. You replace this P is a parabolica. You just look at Borel and then take some take a weight and look at the highest weight vector. So for example, classical modular forms can be viewed as some lowest weight vector of automorphic forms. So here you do similar thing. You look at, you just try to study completed cohomology and look at this space, but it turns out it's much bigger than classical space of classical modular forms. But, the size is really like overconvergent modular forms. So for me, actually, this first time I felt overconvergent modular forms. I don't know. It's a natural object. I mean, it exists for a very long time, but after this, for example, I feel it's for example more natural than Serre-Spaghetti modular forms.
And something like this can be done for other Schmor varieties as well.
So yeah, I think you can do similar thing, but then it will appear. So then the shifts appear. So you have more Broughette stratification, you can express, but you don't understand that. Yeah. For example, I should mention that. For example, in the ordinary case, this is some recent work of Newton, Anna Cariani, and Juan SML Rodriguez Camargo. They just try to understand this, just restrict to the ordinary case, but of course on the integral level, then try to express this as a higher Hida theory. Of course, the ordinary part is just some part of it, but that already gives you some idea what kind of results you should expect. But I would say in general, it's quite complicated. For example, if you even just for GSP4, what appears here is just some spectral sequence, and you don't understand the morphism between them. So there is an answer, but we don't understand the answer.
Ask questions? Okay, if not, let's thank speakers again.
Thank you.
Thank you.